Welcome back to the series on statistical mechanics. Today we will be discussing one of the examples for canonical ensemble, where we will be evaluating the partition function for one of the major examples of canonical ensemble, which is a classical ideal gas. If you remember from our previous episode, we put a background of what does a canonical ensemble means by, what are its characteristics, and we evaluated its partition function. And there we have told that partition function is one of the major fingerprint information for any ensemble system. So therefore, in that episode, we already discussed that if we can find out the partition function for any real system, that would give the most relevant statistical mechanical information on the system. And if you remember, the expression which we derived for the partition function for a canonical ensemble was Qnvt is equal to exponential minus beta ER, of course, summation over R exponential minus beta ER. So this is the expression for the partition function of a canonical ensemble system. So today, as I told you in the beginning, we will be taking one specific case of a 3D classical ideal gas. If you remember, in our beginning episode, we started our discussion on the statistical mechanics by taking up a case of a classical ideal gas. There we calculated the number of microstates possible and all those things, and we discussed also the paradox which is associated with that also, right? Now, so in today, we will assume that our 3D ideal gas is contained in a 3D space, right? So how will I put it? So imagine that our ideal gas is contained in such kind of a 3D system. And if you remember, for any ideal gas, the particles do not interact with each other and they have associated properties which are assigned to it, right? And now the question is that how many microstates are possible in such a system, right? Because if we need to calculate the partition function for any system, first and foremost information which we need is that how many microstates are possible in that system, or more specifically in that system which is positioned in the phase space. Without any explanation, I can write that number as d omega by h raised to 3n n factorial. So this is the number of microstates in the phase space volume d omega. If the volume is d omega, this is the number of microstates. Now the question could be, or you may have doubt that how we reach that number, right? For that purpose, how do we reach that number? We know the Heisenberg's uncertainty principle, that for a single particle, delta Q into delta P is equal to, or of the order of H. The and if I take the n particle system, what could be it be? That could be delta Q delta P is H raised to n. So here we are assuming that it is confined in one single dimension, right? Because delta Q is only about one single axis. So delta Q into delta P is nearly equal to H raised to n for an n particle system, which means that if I take one single particle, even if you in the space, if I ask me what is the volume which that single particle will occupy in that space, my answer would be this H, right? And if there are n particles, its total volume will be H raised to n. And if the n particle system, if we are considering it in the 3D phase space, that can be written as H raised to 3n. So this is the volume occupied by an n particle system in a 3D space. Now the question is that if I give you, say, omega or the d omega volume, what is the number of particles or the number of microstates in that volume, right? Which will be what? Which will be d omega divided by H raised to 3n. Why? Because d omega is my volume and H raised to 3n is the volume of the n particles in the 3D space. That means this will give me the number of microstates in the volume element d omega, right? Now, if you remember the Gibbs paradox, right, we made a correction there. If you don't remember, you have to rewind the previous episode and go back to that. There we made an assumption for an ideal gas system that in order to prevent the overcounting of the system, or in order to account for the indistinguishability of the particle, we have to divide it by n factorial, right? So which means that in the system which is in the phase space system, which is having a volume d omega, the number of microstates will be given by d omega by n factorial H raised to 3n. So that is how we got this number. Now the question could be, why do we need this number of microstates, right? Here I have to invoke something called the degeneracy, which we may not have discussed that time in our discussion along with the canonical ensemble. But from where does the degeneracy thing comes into picture? Here we are necessarily invoking a system, be it classical or the quantum. There are these energy levels, right? And these energy levels, within the same energy level, there may be many closely spaced energy levels. They are so close that they do not possess a separate energy values, but they are closely spaced and they are part of one single energy level. That is what we call as the degenerate energy levels. So therefore, in those cases where the energy values within E are very close to each other, they can be considered as a continuous variables. Especially this is applicable in the case of classical gas situations. So therefore, I can write if you remember, our original expression for Q and Vt was what? Integral 0 to summation over R e raised to minus beta R, ER. Let me rewrite it. Qn Vt is equal to summation over R exponential minus beta ER. This was our original expression. But if we are when we are invoking the classical system, we need to remind ourselves that we are actually dealing with a continuous variable system. So instead of the summation, which is more applicable in the case of quantum mechanical analysis, for a classical situation, it would be more better to or more convenient to use the integral factor, right? Which means that I can write the same expression as Qn Vt is equal to integral 0 to infinity exponential minus beta E. So we are definitely talking about a situation where we are taking all the particles into consideration from 0 to infinity. Now what I was telling is that here this equation may not be sufficient all the time, because the same energy, there may be different microstates with the same energy. So there we have to remind ourselves about the degeneracy levels, and therefore we have to add something more also into this equation, which is we will write it as GD, which means that in an energy spacing dE, I have G number of states, or this is otherwise known as the weight factor. Weight factor of the system, right? So this is now this is our expression. This is our latest expression. Qn Vt is equal to integral 0 to infinity GD exponential minus beta E. So this is our latest expression for the partition function in a typical classical canonical ensemble system. So now we need to introduce this equation into our calculation for the classical 3D ideal gas system. In that case, we will so we have the degeneracy as this one, which means that instead of GD, I can put d omega by n factorial s raised to 3n, and instead of that, and again instead of E, I can write it in terms of the Hamiltonian, right? Which means what? Which means that if I am essentially reminding myself of a situation where the energy is largely kinetic, right? So I don't see any kind of interaction between the particles, so I can neglect all those contributions of energy, because between the particles there is no interaction. So it is energy is wholly kinetic, and therefore I can write the Hamiltonian H, or the energy, is equal to summation over I summation I equal to 1 to n pi squared by 2m, right? So this is my the energy or the Hamiltonian. So we will now modify this expression over here with GD as this one and energy as this one. And what is beta? Beta is equal to 1 by kT. We know it from our previous episode, right? So now let me put all of those things together into one single equation, and therefore I can write Qn Vt is equal to 1 by h factorial h raised to 3n integral 0 to infinity exponential minus beta h of Qp, because we are necessarily in the phase space, h of Qp d omega. So, this is the expression for the for the partition function which we need to expand more specifically for the 3D ideal gas now, right. Now, we have this d omega over there, right. What is that? D omega is my volume. What is the space which we are talking about? We are talking about a phase space. What are the constituents of that phase space? We have a Q space, right, which is Q space means which is about the distances, right, and then there is a P space, momentum space. So, we are essentially carrying out this integral over two different spaces. One is over the Q space and another is over the P space, right. So, let us separate them in that for those things in that expression. So, how do I modify that? Then in that case I can write this as equal to 1 by n factorial h raised to 3n integral 0 to infinity exponential minus beta h of Qp product over I d cube q d cube p. So, that I d cube q I, since I have the product over I need to put the I over there. So, the product over the Q space and the P space or the momentum space. How do we proceed then? Now, we have an integral in place, we have d cube q, right. If we carry out this integral in the space over the space coordinates or the distance coordinate, I can write them as triple integral dx dy dz is equal to v raised to n, because that is the total volume of my system, and therefore dx dy dz is equal to v raised to n, which means that if you remember that volume which I draw in the beginning of this series of this episode, there is some volume in which this ideal gas is going to occupy the system, and the volume of that box was V. Since there are n particles which are non-interacting, each particle is allowed to occupy the whole space. Therefore, instead of V, we have V raised to n. So, that is how the triple integral dx dy dz is equal to V raised to n. Now, we need to make the integration over the momentum space, right. How do we do that? For that purpose, we imagine that there is a momentum space. So, in that momentum space, we need to imagine that there is a volume for the system, right. There is a volume corresponding to that momentum space. So, let's calculate it, right. So, this is the sphere in which, say, our system is occupied, and we are cutting a shell out of that sphere. Say if my radius is p and and the inner radius is P minus dP, right, which means that what? Which means that the thickness of this space is dP. So, what do I do? I need to calculate the volume of that that shell. So, which I can do it as 4 by 3 pi p cube minus 4 by 3 pi p minus dP the whole cube, right. This is the volume of the ring or of the shell which we are considering. So, so you can carry out this one. How do we do that? 4 by 3 pi p cube minus 4 by 3 pi p cube minus 4 by 3 pi p squared dP minus 4 by 3 pi p dP squared minus 4 by 3 pi dP cubed, right. So, from there, right, there's a minus in the outside which you know, and if we neglect all we know that the dP, the dimension of dP is really small, right, and therefore I can consider that those factors which are of dP squared and dP cube I will neglect. Again, these two factors will get cancelled out. The only factor which will get remained is this one, 4 by 3 pi p squared dP, and therefore I can write the integral value as equal to 4 pi p squared dP. Yeah, so there's a 3, right. I need to multiply it by 3 also, that which I forgot. So, therefore, the volume of the shell which I have imagined, I can write that as equal to 4 pi p squared dP, which is what? Which is my triple integral dpx dpy dp z. So, triple integral dpx dpy dp z, now we evaluated that to be equal to 4 pi p squared dp, and in triple integral dx dy dz is equal to v raised to n, and therefore over here instead of d omega, now we are in a position to substitute that over there, right. So, what we need to do now? We need to modify that expression over there. Let me do that. In that case, I will be able to write it as equal to 1 by n factorial, or we have the v raised to n. V raised to n, n factorial, h raised to 3n, triple integral 0 to infinity, exponential, instead of beta we can substitute the 1 by kt at any point of time, but minus beta, h is equal to, we know that it is summation over I pi squared by 2m, and the 4 pi p squared dp also, right. For pi p squared dp, and whole thing raised to n, right. So, therefore, so this is the expression now for the QNVT for the 3D ideal gas, and then we need to do this integral. Now, if I do the integral, now I will get this based on the gamma function, exponential e raised to minus alpha y squared y dy which you need to do the which is a simplified step for doing that thing. In the Patria, if you look into the appendix, on the Patria is the book on which we are basing this course. If you look into the appendix of the Patria, you will see the derivation for those people who are interested. But that mathematical derivation is not our concern over here, so I am not going to do that. So based on that substitution, if I do that gamma function substitution over here, I can make this integral much more simpler, and I can write it as is equal to v raised to n by n factorial h raised to 3n. So we are carrying out this integral, right? So which we can write that as 2 pi m kt raised to 3 by 2. So this is this integral 0 to infinity exponential minus beta pi squared by 2m 4 pi p squared dp, and then that raised to n. So this is the expression which you will get for a 3D ideal gas system, the partition function. If I look it more closely, I can now write it, I can now take this v and the h inside, right? Inside the expression, and I can write it as 1 by n factorial v by h raised to 3 2 pi m kt raised to 3 by 2 raised to n, right? Right. So either I can close it here, or I can tell more information over here, because the moment I see this 2 pi m kt over there, I am reminded of something else, which I call it as what? As the de Broglie wavelength. So what is de Broglie wavelength, which I will tell? So this 2 pi m kt raised to 3 by 2, I can simplify it based on the de Broglie wavelength and write the expression as Qn Vt is equal to 1 by n factorial v by lambda raised to 3 by 2, lambda raised to 3, because h by root of 2 pi m kt, that is what the lambda is equal to h by root of 2 pi m kt. This is the expression for what? Our de Broglie wavelength. This is the expression for our de Broglie wavelength. So if I have substituted there 1 by n factorial v by lambda cube raised to n. What is de Broglie wavelength? De Broglie wavelength is a very important information in the whole physics itself, because that is the distance which distinguishes between, or puts a borderline between distinguishable and the indistinguishable systems, right? So if the distance between two particles are more than or bigger than the de Broglie wavelength, we generally we can classify that system as classical systems, and in the other case it is generally quantum mechanical system. So de Broglie wavelength That is the significance of this de Broglie wavelength over here. And again, I can write the same expression in terms of something else also, which I will write it as QnVT is equal to Q1 raised to n divided by n factorial. What is Q1? Q1 is called the single particle partition function. Single particle partition function. What is single particle partition function? It is basically a factor which is similar to the partition function, but it basically refers to the contribution of a single particle to the overall partition functions of a system, right? For example, let's say a single particle may be divided into different energy levels. So this single particle partition function will tell us how much weightage is there in various levels. So basically it's a contribution of single particle to the overall partition function of a system. So we can write Qn Vt is equal to Q1 raised to n by n factorial. That is another way with which we can explain a single particle, the partition function for a 3D ideal gas system. Yeah, so today therefore we saw how does a 3D ideal gas system can be analyzed based on the canonical ensemble and how to evaluate its partition function. We evaluated the partition function based on its de Broglie wavelength and in the case of and with the case of a single particle partition function, which these expressions can be used for many specific cases of distribution systems, which are really useful for the physical understanding of any real world examples. So this ideal gas becomes the very basic or the most generalized analysis of any kind of canonical ensemble system. There are many examples possible in the case of canonical ensemble systems, right? We will not be discussing many examples, but in the next episode or in the coming episode, we will be discussing one or two more examples which are more generalized or which are of more general applications for any statistical mechanical systems, which we will see in the next episode. Thank you.